Today we're going to be looking at how to do some basic graphing with rational functions. Now, part of what we're going to look at today is actually a review of what we talked about very briefly in our first unit with parent functions, but we do need to add some additional vocabulary and additional ways that we can think about these functions as we're moving into our next unit. So let's jump in. Let's look at what we've covered before, and then we'll add on our new piece. So the original function that we looked at when we were looking at parent functions, very first unit of the year, looks like this guy. So any rational number, again, is basically something we can write as a fraction. So this basic parent function would actually look, with no modifiers whatsoever, would look like f of x equals 1 over x. And then we can use the same variables as we have with previous functions to talk about our different transformations. So you'll notice we have an h, a k, and an a in there. And they do exactly the same thing as our variables have in other functions, especially with, you probably remember our absolute value and our quadratic functions most specifically in this format. And so the a value, again, two different things that we can consider with that. We can consider either a positive a value or a negative a value, and that determines which direction our graph is going to be facing. So if we had a plus a value, so even just a +1 or a +1, then our graph is going to look just normal, whatever our original function should look like, which we'll graph on the axes below. If we had a negative a value, like a -1 or a -2, that means we're going to do a vertical flip. In other words, flip over the x-axis. So up to down. If we have different values in for a, it can tell us how we're stretching or shrinking, or technically how we're dilating that figure. So if we have an a value that's greater than 1, like a 2 or a 3, that's a vertical dilation where we're stretching it, versus something that's smaller than 1, a fraction between 0 and 1, would be a shrink. But we're always dealing with a vertical dilation, never a horizontal dilation. If we had a b value, a coefficient right in front of the x, then we deal with a horizontal transformation. But again, we're going to leave those to future math classes. Our h and our k still have the same behavior as they did before. So if we had a negative h value, that means we end up moving right. If we had a positive h value, it means we move left. If we have a negative k value, that means we move down. And a positive k value means we move up. So before we look at our new pieces of information, let's just remind ourselves of what this function graph would look like. So down on the graph right below, let me change my color over to red. So our f of x equals 1 over x, parent function, had two different branches to it. So it went from 0.1 and kind of curved this way, and in the bottom left quadrant, except I need to redraw that because again, we want to make sure we're hitting that 0.1 away from the origin. There we go. And so any modifications that we're going to do to this graph start from this picture. But this picture, it does look a little different. So it has a break in the graph. And again, we mentioned this really quickly during our parent functions unit, but now we're going to have to start using this more often. So that kind of imaginary line that this graph is not going to cross. And again, it has an imaginary vertical line and an imaginary horizontal line. Those are called asymptotes. So if we go back up to our definitions, technically this is called a discontinuity. So this is a place where we have a jump in the graph. And we talked about this a little bit when we were talking about domain and range. So still, an idea of we have this jump in our graph. We have two different kinds of jumps that we're going to talk about this unit. Something called an asymptote, which again is that imaginary line that our graph cannot cross. We can have horizontal, vertical, and slant asymptotes, but in this unit, and actually in this course, all we're going to look at is horizontal and vertical. So I'm going to go ahead and cross out slant asymptotes. You'll take a look at those perhaps in Algebra 3 trig and definitely in pre-calculus if you move on with algebraic courses. We also have a hole. And again, we talked about this briefly, but we're going to learn later on in this unit how we can actually find this algebraically on a graph. Today, though, all we're going to talk about is if we're given a standard graph in that transformational form, where are our asymptotes? And if I have a picture of a graph, being able to name both asymptotes and holes. So let's start with our first example. We are going to graph and describe the function f of x equals 1 over x minus 2 plus 3. So there's two things that happened on this graph. So the first thing is that -2, which means we're going to move right 2, because again, we always go opposite from the sign if it's inside our function. And then the +3 means we're going to move it up 3. So from the red graph, our basic rational function, we're just going to take every point and move them in those directions. Now, when we're looking at this, though, it's actually a little bit easier to draw our asymptotes first. So I'm going to draw our asymptotes in, let's actually change over to green. Alrighty. So green asymptotes. Originally, our asymptotes are sitting right on the axes, on the X and Y axes. So I didn't bother drawing them with the red graph because it's so well centered on the graph. But for our new graph, our asymptotes, again, we're going to draw them in green. I have to go right 2 from the Y axis. So that means I'm going to have an asymptote along this line. Because it's a vertical line, every time we graph those lines, those are always going to be x equals. And because we moved it to the right 2, our vertical asymptote is x equals 2. Now the +3 says we have to move the whole graph up 3. So again, original asymptote was sitting right on the x-axis. We're moving up 3 units from that. But again, thinking all the way back to our original unit with parent functions, our horizontal lines, they're always crossing the y-axis. So that one is y equals 3. And so let's go ahead and draw on our graph, and then we'll talk about domain and range. So our our graph, again, I'm just translating the red graph up from where we started to our new location. And so my kind of point of reference is 1 point up to the right and 1 point down to the left from the center of those axes where they intersect. And so our new graph is going to live up here. So the purple graph is our 1 over x minus 2 plus 3. So then our domain and range, again, we want to express that we have these hiccups. We have these places along the asymptote where our graph doesn't exist. And so actually, if you already know what your vertical and horizontal asymptotes are, that makes writing out our domain and range very easy, because you'll notice the ends of the graph keep going in both directions. However, if for our domain, we never cross that vertical line of x equals 2, that means that's the one value our domain can't have. So our domain would be x is such that x cannot equal 2. Again, same number we had with our asymptote. For our range, again, our horizontal line that we can't go across, so moving up and down on our graph, we can't cross that horizontal line, and it's a y equals. So our range, we have to use everything except that value. So f of x cannot equal 3. So when you're doing these problems, if you can figure out what your discontinuities are first, all you have to do to list out your domain and range is say, I just can't use those values. Alrighty, next example. Here we go. So state the domain, range, and asymptotes of the functions. So now in example 2, we're going to graph the function f of x equals 1 over x plus 2 minus 2. And so let's first determine where do we need to move this graph. Now, as we looked at in the previous example, we're pretty much with our asymptotes imagining, well, if we started from the axes, where are we moving them from there? So with our first value, our h equals positive 2, that means we're going to have to move to the left 2. So we're going to take our vertical axis and go 2 units to the left to do our first asymptote. So our vertical asymptote, 2 units to the left, that means we're looking at x equals -2. Our -2 in the K spot means we move our graph down 2, basically from our axes. So down 2 units, there's our horizontal asymptote, which is going to be y equals -2. They both happen to be -2, but that's okay. So now when we graph out our function with our a value, we have no changes. So because that's a +1, we don't have to flip, we don't have to stretch, we don't have to shrink, we don't do any of that. So that means we're going to go out 1 to the top right and out 1 from the bottom left and draw in the branches of our graph. Alrighty, so now we can do our domain and range. And again, it's really just stating here the values that we have to skip from our asymptotes. So our domain x is such that x cannot be -2, which we had from our vertical asymptote. As we're moving from left to right, we have to skip that line. And then our range, f of x, is such that f of x, or our y values, cannot equal also -2. But that's because as we're going up along our graph, we have to skip over all of the y equals -2 to continue on to the next portion. Alrighty, example 3. So this one does have a change to it. So this -1 in the numerator, that's our a value. Because a equals -1, we're going to have a vertical flip. So we're going to change our branches. Instead of having a branch going to the top right and to the bottom left, they'll be flipped over. Our +1 in the H spot means we're going to move left 1, and the +2 in the K spot means we move up 2. All right, so draw your asymptotes first. So left 1 from the y-axis, vertical asymptote of x equals 1, excuse me, -1, our line that we can't cross. Then our horizontal has to go up 2. So horizontal asymptote y equals +2. And then again, we flip-flop. So instead of going up to the right, we have to go down to the right and up to the left. And we still had a 1 value. So that means I'm not stretching out or shrinking or anything. Just tells me I flip the direction of my parts of my graph. So then domain, here we go. X is such that x cannot equal which value? -1 right from the vertical asymptote. And then f of x is such that f of x, or our y values, cannot equal 2 because of our asymptote. So what if we're not actually given an equation? We can still describe what's going on with these functions if we're just given a picture. And these actually have one more piece layered in. We haven't talked about holes yet, so let's check those out with the next 2 examples. Okay, here we go. So examples 4 and 5, we're going to describe each function graph. And actually, let me shrink this down a bit so we can see all of our info at one go. Okay, so 5 things for each example. And you'll notice I listed horizontal, vertical asymptotes and your hole first, because again, that's going to tell us what values we cannot use for our domain and range. And so we don't actually have the asymptotes drawn in on this. So we need to think about, well, what imaginary line can we not cross? AKA, which line, horizontal or vertical, is our graph getting really, really close to, but never crossing? And so in number 4, if I'm looking at my horizontal asymptote, well, let's see, does it look like the graph ever crosses the x-axis? It's really, really close at the ends, but it's never going to cross it. So let's go ahead and draw that in. So horizontal asymptote is right on the axis, so that means we're going to have y equals 0. Okay, vertical asymptote. And again, once you draw one of the asymptotes in, it sometimes makes it a little easier to see the other. Okay, what line does it look like we can't cross, but we get really, really close to? So we're getting really close to that -2 line. So we'll draw that in. And so our vertical asymptote x is equal to -2. Alrighty, and a lot of times on your graphs, these might be already drawn. So I think on your practice, I think most of these already drawn in as a dotted line. So you'll already have that visual to help out. Okay, last thing new is hole. So we have a skipped point on our graph. Now for this one, again, I'm gonna have to estimate it. So it looks pretty darn close to, going about 1/4 of the way up. So I'm going to estimate that my hole, so this empty piece right here, where we're kind of missing that point and we don't have it anywhere else, he's sitting at the point 2 and about 1/4, so 0.25. And again, if it hits right exactly at a grid space, that makes your job even easier. So now that we know all the places that our graph can't touch, now we can write our domain and our range. So again, domain is always about your x values. So the question is, which x values can we not use? Well, we can't use the vertical asymptote value. So x equals -2, that translates to x cannot be 2 for the domain. But what other x value is missing? We can't use the x value from the hole either. So we're also going to list out 2 from the x coordinate of our hole. For our range and f of x or y values, what can we not equal? Well, our horizontal asymptote, y equals 0, that means we can't cross that line, so we can't be equal to 0. But what other y coordinate can we not use? Yeah, at 0.25, or about 1/4. Okay, let's check out our last example. So again, let's look for our asymptotes and our holes first. So I'm looking at the ends of the left branch and the right branch. And it looks like, again, my graphs are getting really, really close to the x-axis. So if that's one of our asymptotes, that means our horizontal asymptote, y equals 0. Again, horizontal lines are always y equals 0, vertical lines are always x equals 0. So vertical asymptotes, this one actually has 2. Where do you think they are? So we have that line at -2 that we don't cross. And we have the line at +2 that we don't cross. So vertical asymptotes, we have 2 of them. So x equals -2 and x equals +2. And again, we'll look more at the algebra when we come back from Thanksgiving break to see how this is actually going to look in the equation, but you're going to have a chance to do a preview of it real quick. Okay, our hole, again, there's only one point that we're missing on our graph, and it's at a nice set of exact coordinates. So our hole is at 1, -1. So now we can write our domain and range values or expressions. Domain, again, all the x's such that x cannot equal, well, what x's can we not use? From our vertical asymptotes, we can't use a -2, and we can't use a +2, and we also can't use a 1 from the x coordinate on our hole. I'm going to go ahead and write them in numerical order. Doesn't really matter, but the mathematician in me wants to have everything in order, least to greatest. Range, same thing, all values that we can't use. So f of x is such that f of x cannot equal which y values? We can't use the 0 from the horizontal asymptote, and we can't use the -1 from the hole. So I'm going to list -1 and 0, again, just to go in numerical order. Now, if you don't believe me with this, if you want to see how this connects to the graph and how I actually created these graphs on Desmos, if you actually click on the link in your notes, which is right below there. So in that graph, I've actually graphed both of those expressions. Now, the tricky thing with Desmos is it doesn't actually show you where the holes are, because again, those discontinuities, there's a really difficult for that system to graph. And so with each one of these, I do have an extra point graphed, but that you can just use to verify, did we come up with the correct coordinates for our holes? Alrighty, as always, let me know if you have any questions, and if not, get started on your activity for practice today.